Welcome viewers to the last segment of the fifth lecture for the online series of lectures for the course of Algebraic Topology 2. So in the previous segment we proved that the right hand square here in this diagram uh, also commutes. Okay, in other words, we proved this equality. Okay, which means that this diagram here is a commutative diagram, and and uh, in other words, it means that these two maps, phi and psi, are augmentation preserving. Okay, the maps phi and psi preserve the augmentation map. Okay, good. Now, one also notices in this context that this bottom sequence here in this commutative diagram is an exact sequence. Okay, so let us try to see how we can prove that this sequence is an exact sequence. One also notices here that the sequence 0 to z, from z to z direct sum z, and then from z direct sum z to z, and then from z back to the trivial group. This map is phi minus 1 and this map is psi minus 1. We want to see that it's an exact sequence. Indeed, phi minus 1 is injective and psi minus 1 is surjective. Follows from their definitions. Okay. Indeed, phi minus 1 and psi minus 1 are injective and surjective respectively. Okay, and how do you prove the exactness at this site? Note that kernel of psi minus 1 is equal to, right? So let me write down the definition of phi minus 1 of n is n comma minus n, and psi minus 1 acting on the pair m and n, m comma n, spits out m plus n in the additive group of integers. So kernel of psi minus n is the collection of pairs m comma n in the direct sum of these two copies of z, such that m plus n is 0, right? And it's the it's the set containing all pairs n comma minus 1 such that n is in the group of integers. Okay, and we know that from the definition of phi minus 1, we know that this is image of phi minus 1. Okay, so this way we see that kernel of psi minus 1 is equal to image of phi minus 1, which proves that this sequence is a short exact sequence. Hence, one has the following short exact sequence of augmented chain complexes zero to C of A comma epsilon A. This is an augmented chain complex, and from this augmented chain complex to the augmented chain complex C of K0 direct sum C of K1 comma epsilon 0 direct sum epsilon 1 via this chain map phi, and then from this augmented chain complex via psi to the augmented chain complex C of K comma epsilon, and then back to the trivial chain complex. Okay. So we thus see that this is a short exact sequence of augmented chain complexes. Okay. Now applying the zigzag lemma, one obtains the Mayer-Vitteris sequence in reduced homology. Okay. Which looks like this, the one that I'm writing now. Dot 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 dot, and then we have H tilde P plus 1 K0 union K1, and that leads to H tilde P of K0 intersection K1 to H tilde P of K0 direct sum H tilde P of K1 to H tilde P of K0 union K1 to H tilde P minus 1 of K0 intersected with K1 dot 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 like that, right? QED. Good. So Mayer-Vitteris sequence done. Now an important fact which is trivial as well. A trivial fact which is important. 0 to A1 to A2 to 0, and the map, the homomorphism between the groups A1 and A2 is denoted by phi. If this is an exact sequence of abelian groups with phi being a group homomorphism, then phi has to be bijective. In other words, phi will be an isomorphism. It follows from the fact that kernel of phi is 0. In other words, phi is injective because kernel of phi has to be the image of this map on the left, on the far left, and the image of the map on the far left is just 0. So the kernel of phi is also equal to 0, which means that phi is injective. And if well, here exactness at this site A2 tells us that image of phi here is going to be equal to kernel of this map, and kernel of this map is the whole of A2, which means that the image of phi is the whole of A2, meaning leading to the fact that phi is surjective as well. So phi is a bijective map, phi is a homomorphism, and hence phi is a bijective homomorphism, meaning that phi is an isomorphism. In this case, phi turns out to be an isomorphism. Okay. Right. Now definition of suspension. You had an exercise worked out before on suspension. Now I'm giving the definition again here, so let me draw a picture. So here is a two-dimensional complex. We denote this complex by K, and there are 2 points here. One is denoted by W0 and one is denoted by W1. So we form the cone W1 star K, and it looks like this. Okay. And then we form the cone W0 star K, which looks like this. So this is the figure of a suspension. Let K be a complex like we have here. Let W0 star K and W1 star K, like we have in this figure, the second figure, let these two cones, so these are two cones on K whose polytopes intersect in this topological space, the underlying space of K alone. Okay. All right, so it's immediate from this picture that the polytope of the upper cone intersects the polytope of the lower cone the in just the underlying space K of the complex. Okay. Um, then S of K is the union of these two cones, W0 star K union W1 star K. Okay. This is a complex. It can be shown that this is a complex. It's a union of two cones that intersect at the the at the complex, at the underlying space of the complex K, and it's a complex by its own right. It is called the suspension of K, the suspension of K. Given K, S of K, which is the suspension of K, is defined uniquely up to a simplicial isomorphism. Which means that we can change W0 and W1 and get different cones like W0 star, W0 star K and W1 star K. By changing W0 and W1, we can get different cones. And the suspension that we get after taking the union of those cones, then the suspension, this family of suspensions are simplicially isomorphic. Okay. Now the third theorem is about the suspension. Theorem 3. If K is a complex, then for all P, there is an isomorphism HP tilde of the suspension of K to HP H tilde P minus 1 of K. Okay, there is an isomorphism. Okay, so here is the proof of theorem 3. Let K0 is equal to W0 star K, and K1 is equal to W1 star K. Then the union of these two cones is equal to the suspension of K, right? According to the definition of suspension. And we also know that in fact, which follows from the definition of a suspension, that the the two cones intersect at the complex K. Now, a Mayer-Vittori sequence in reduced homology then yields H P tilde of K0 direct sum HP tilde of K1 map to HP tilde of the suspension of K, which is the union of K0 and K1, and that gets mapped to H tilde P minus 1 of K, which is the intersection of K0 and K1, and that gets mapped to H tilde P minus 1 of K0 direct sum H tilde P minus 1 of K1. Okay, so now from Theorem 3 of Lecture 2, we know that a cone is acyclic. A cone is acyclic. In other words, the reduced homology group of a cone vanishes for all P, right? It means that H tilde P of K0 is equal to 0 and H tilde P of K1 is equal to 0 for all P. So which means that the two terms in this sequence, in this exact sequence, because it's a mere Viteri sequence and it has to be exact, and the two terms on the far left and on the far right are 0. So we have this exact sequence 0 getting mapped to H tilde P of S of K to H tilde P minus 1 of K to 0. Okay. So from the exactness of this sequence, it follows that this map has to be an isomorphism. So, which we discussed before the definition of suspension, which we call the trivial fact. Follows from the exactness of this sequence that this has to be an isomorphism. It follows that from the exactness of the above sequence, it follows that that the map from H tilde P of Sk to H tilde P minus 1 of K is a group isomorphism. Okay, so Theorem 3 is an application of mere Viteri sequence. Okay, so this ends lecture 5. Before closing this lecture, I want to suggest a few exercises. Suggested exercises. They're suggested from section 26, problem number 1. It's very important to work out this problem, and problem number 2. So I give you just 2 problems from section 26. Okay, thank you very much for attending the 5th lecture.